Out to the last talk of the day. I shall try to make it exciting and exhilarating and worth your while. So the first thing to say is this is joint work with Alex Thierry, who's in the audience. And in fact, the key idea, Discrete Bouncy Particle Sampler, that I'll be describing was his idea. Second thing to say is I've actually changed the title of the talk from the Discrete Bouncy Particle Sampler to a Discrete Bouncy Particle Sampler after Alexandre Bouchard's talk on Monday, where he described a different Discrete Bouncy Particle Sampler. So I will actually try and describe both of them. I'll mainly be talking about ours, obviously, but I will try and briefly describe his, and so you can see the differences. Next. Yes, so what I'm going to start out with is describe the Bouncy Particle Sampler, very briefly indeed, which is a continuous time algorithm. Then I'll describe the guided random walk of Gustafsson, which Christoph talked about yesterday as well. I'll talk about it slightly differently. And then hopefully you'll be seeing we're crying out for a Discrete Bouncy Particle Sampler, which will then be going on to our work. So, firstly, the Bouncy Particle Sampler, BPS. What this is a continuous time Markov chain, okay? And it's on an extended state space. So your x, you've got a pi of x you're interested in, but you've also got a velocity u, a unit velocity, so it's on the unit sphere. It's got a uniform distribution. So you've got a joint Markov chain on x and u. And what it does, okay, here's where we start, where I put the red dot. And it's got this velocity u, and it just keeps going along the state space. So these are contours of the state space. For demonstrations, I'm just going to use 2 dimensions, occasionally 3, and then real results will be higher dimensions. And it keeps going along the same path, so x is changing, u is not, until a red dot, a bounce, happens. Okay? When do these bounces happen? A bounce happens if you're going uphill, it won't happen at all. As soon as you start going downhill, it will happen, and the chance, it's a Poisson process, and the rate of the Poisson process is the steepness with which you're going downhill on the log posterior. Okay? So if you're going fairly steeply downhill, you can be pretty sure you'll get a bounce soon. All right, so if we go on, hey, I've had another bounce. We'll describe exactly what's happening in the bounce, so I'll show you a picture in a second. But basically, you look at the gradient, you draw a tangent plane, and you bounce off the tangent plane. Okay, and that's gone along, it went uphill, it was fine, then it started going downhill, and there's a bounce. This Poisson process is hit, and there's another bounce, and another bounce. It keeps going, and you keep going for some time. I think that's as far as I've got it. So it won't, in fact, end in a bounce, but you say, I'm going to integrate this forward for some particular time, 100 seconds, whatever, 100 sort of seconds in there, not in CPU time. And then you use a time average, because if you ignore the velocity, this has a stationary distribution, it turns out, pi of x. All right, it's a continuous time Markov chain with the right stationary distribution. So you can just use a path average to estimate any integrals you're interested in. So that was the Bouncy Particle Sampler with no notation. There will be some stuff coming in a minute. All right, so exactly the bounce, just to demonstrate. Here it is coming in, the arrow's just showing the direction. It comes in, your Poisson process hits because you're going downhill. Bang, I know there's an event here. I draw the contour through that point. So the contour of my log posterior through that point. I create the tangent plane, and I bounce off it, literally. The angle of incidence equals the angle of reflection. O-level physics, GCSE physics. All right, and off I go in this direction. So that's the Bouncy Particle Sampler, and it's continuous time. So what are the advantages of non-reversible methods? So I'd say, it's non-reversible. It's got a sense of direction. It knows where it's going, even if the posterior is completely flat. And that means you don't get the meandering random walk behavior. Okay? So in fact, think about when the posterior is not completely flat. If you've got a d-dimensional space, well, it's going uphill in one direction, and locally it's flat in all d-1 other directions. So you've basically got meandering in reversible methods on d-1 dimensions, and sort of it can do something exciting in one dimension. Whereas that's for reversible methods. For non-reversible methods, they've got this sense of direction, so they're going to hopefully explore the space better. Okay, now That's any non-reversible, anything with a sense of direction. The one I've just showed you, the BPS, is continuous time algorithm. And there's another continuous time algorithm, the zigzag sampler. And the only thing I needed to know there was grad log pi. Yeah, I just needed to know it, because that, if I was going downhill, that told me when a bounce would happen. And I looked at grad log pi then, and that tells me the angle I'm going to bounce off at. That's all I needed to know. So there's another advantage of continuous time methods, which was especially in this paper. Everyone here is in the audience. Most of the people here are in the audience as well, where you can use subsampling and get a noisy but unbiased estimate of grad log pi. And that can lead to very efficient inference, at least for simple models, and when you've got big data, so lots and lots of tall data. But what I glossed over, we needed this Poisson process whose rate depends on where you are. It's how fast you're going downhill. Okay? So we got to simulate that from an inhomogeneous Poisson process. And very simple models, you might be able to solve it exactly. Slightly less simple models, you might be able to get a bound and use thinning, as was described on Monday. But what if you're just getting grad log pi? That's all you can get. You can evaluate pi of x, you can evaluate grad log pi. You haven't got much of an idea of getting bounds. So if we had a discrete time non-reversible algorithm, then we wouldn't need to simulate bounce times. We'd be moving through the space in a nice, purposeful manner. That would be great. I wouldn't need to simulate from a Poisson process. But, all right, the disadvantage is I wouldn't be able to do this nice big data trick that Joris et al. Have. So where we think our algorithm will target is sort of more complicated targets, basically. Two uses of the word target. So I'm going to describe, again, the guided random walk. And this is because it's a key component of the discrete bouncy particle sampler. I'm going to use slightly different way of thinking about it to Christoph. I'm going to think of it as the composition of two separate reversible kernels. So each of those is preserving pi, so if you do one after the other, that's going to still preserve pi. And yet it's not going to be reversible. I'm also going to do something silly with it, because it will help us later. So Gustafsson never intended, I think, for this to be a two-dimensional algorithm, in that he was imagining if you had more than one dimension, you would run this separately in each dimension. I'm not going to do that, and I'm not trying to make him look ludicrous at all. It's so it'll help us understand. Okay, so I'm going to describe it in multiple dimensions. We've got this unit velocity, u0, and we're going to pick a speed. So delta, imagine our actual speed is delta times u0. u0 is the unit velocity. What we're actually managing to do is delta. And every 1 second, we'll move a distance delta. And there's going to be an extended target, and it's going to be a bit silly this time. It's going to be pi of x. And then what can the velocity be? Well, with 50-50 probability, it'll either be u0 or minus u0. We'll either be going this way or this way, and we're never going to go in any other direction. Okay, so what's an iteration? Well, the first thing is we'll just make a proposal. We'll propose changing from position x and velocity u to position x plus delta times u and velocity minus u. And the key idea is if I do that proposal twice, so if I'm now here, then I'll add delta times this, so I'll go back to x, and I'll flip minus u back to u. I'll get back where I started. So this is reversible. It's basically saying I'm here and I'm proposing moving to there with that velocity, or I'm here with this velocity and I propose to move to there. So you're going, it's a reversible, proposal. And because of that, I can just accept it, just like with the random walk, look at the height of the posterior at the proposed, height of the posterior at the current value, and that on its own will give you a reversible algorithm. It won't do anything that's sensible, but it will preserve pi. All right, so that's one reversible kernel, which Christoph was calling QP, I think, or PQ, QP. Here's the second reversible algorithm, and it's the flip move that Christoph described yesterday. So I'm at position x with velocity in that direction, and I just say, let's change my velocity to be the opposite direction. Right. Now, what's the net effect of these two things? All right? If I propose this change, I go from x with speed u to x plus delta u with speed minus u. If I accept it, then I'm now here. And now I'm going to flip the velocity, so I end up x plus delta u and my speed is still u. My velocity is still u. So that's saying from here with this speed, I'll propose here with this speed, then I'll flip if I accept it. So I've just moved, and I'll just keep doing this over and over. However, if I reject the first proposal, here I propose to move there, but I reject, so I just flip the velocity and I'll end up going back the way I've come. Okay, so the composition, even though this one seems silly, I'm just proposing going back the way I've come, because I have this second kernel which flips the velocity, it actually means here with this velocity, and if I keep accepting, I'll keep moving. Point. Oh yeah, no, that's what I've done. I've pointed out the net result of these two. So there's a few italics instructions to self, which I hope they make sense to me. Right. In the demonstrations I'm going to use just for this, for several reasons, I'm just going to use a target which is not a Gaussian. It's just got x to the 4 instead. And there might be different scale parameters. For visualization, as I said, I'll use 2 dimensions and 25 for runs. I've done also with 100. We've also done different targets just to check things make sense and follow. Okay, so here's a quick guide to Gustafson's algorithm, guided random walk, in a place it was never intended to work. All right, so here's where I started, and the black line is now the velocity, which is pointed in that direction, so that's u0. All right, and it moves delta times u0, so that's the proposed value. Oh, that's been rejected, okay, which was minimum of 1 and the ratio of posteriors. It's downhill, had a chance of being rejected. So what it's then done is saying, oh, I've had to reverse the direction. All right, I rejected that, so I haven't moved there. I reversed the direction, and I'm now proposing that. Oh, that's good, I accepted it. So I keep going with that velocity in that direction, propose this, or it looks a bit downhill, and sure enough, it's rejected. So now I've reversed the direction, so I've proposed going here with the reverse direction. I keep going, now I'm proposing here again. I managed to go past that this time. All right, reject, go back the way you came, and so on. See, obviously you can see it's not going to work. It's not going to do anything exciting. It's just going to keep going back here. It'll be reducible. It won't even at all get even out there. But that's the guided random walk and how we'll need it to behave. So what am I mainly hoping to talk to you about? So or in fact, a discrete bouncy particle sampler. And then on its own, it's not going to work. And I'll show you some reducibility problem or near reducibility, which is similar to that you see for the bouncy particle sampler. And solutions, one is similar to the Wu and Robert paper that was archived a couple of weeks ago. Timing. And another one is the same, but for the discrete case, as this algorithm that was, a few months ago archived. I'll talk about tuning the algorithm, and I'll talk about how we don't actually need to evaluate the whole of grad log pi. We can just take its component in 1 or 2 directions and still get a valid algorithm that might actually be beneficial. Okay. So the discrete bouncy particle sampler, how's it going to start off? Right. Instead of now just a continuous time algorithm, we're going to be doing jumps, just like in the Gustafson thing. So we might have started out here, we've jumped to here, we've accepted, we've jumped to here, we've accepted, we've jumped to here, we've rejected. So remember, it's going downhill, so you've just got the ratio of the posteriors as your acceptance probability. We've rejected. So we're going to draw a contour through here, and what we'd like to do is angle of incidence, angle of reflection. Here's the proposal. But should we just accept it? Should we have a chance of rejecting? How do we do it? Yeah, this is where we'd like to move to, because that's exactly like the bouncy particle sampler, but in discrete time. How do we do it? Okay, so here's Alex's insight. So we've got this delta, we've got a u0, our starting position. its target, however, the velocities are obviously going to change now. It's not just going to be either u0 or minus u0. So the first few sections are exactly the same as Gustafsson, yeah? We just keep proposing an update. We accept it with that probability. And if we accept it, basically, we've been here with this velocity. We'll go to here. We'll go to here until there's a rejection. And here's, it's the Tierney and Meary delayed rejection algorithm. Okay? So delayed rejection is basically you can propose in any MCMC, you propose, and if you happen to get a rejection, you can try another proposal. You just have to change the acceptance rate for that proposal so you still satisfy detailed balance. So actually, you go back a second. I need to point out, I've called this thing alpha, alpha from x to x prime. So that's this stage 1, if you like, acceptance rate. Now, one other thing to point out. Here, this is grad log pi is in this direction, the gradient is this direction, this is perpendicular. So if the blue is the same height vertically as the black, then the log posterior is going to be at about the same value. Yeah, they're in the direction of the gradient, they're about the same distance from the red point. Hope that makes sense. Okay, so delayed rejection algorithm. Oh, right, we've rejected there. Well, that doesn't matter. We can try another proposal, and then we've got an acceptance probability, which we'll get in a second. Okay, the proposal is going to be, I mean, this is the equations for it. In a way, the equations don't matter. It's that bounce. Yeah? But it's, you were coming in with this direction. The proposal to make it reversible will be coming in from here with this direction. Yeah? And then we'll do a flip move at the end. Okay, so that's basically the bounce proposal. And these are just sort of arguments, so maybe you can see that it's going to be reversible. It's pretty obvious if you're here with that direction and here with that direction. Obviously, each of these is going to go to the other. And the acceptance probability to make the whole delayed rejection thing reversible turns out to be this. You have to look at the posterior at your final proposed, so it's double primed, posterior at your start. And then the acceptance ratio, well, this was the one you had before. It's now on the denominator. And the equivalent acceptance ratio if you had started at x double primed, so the blue point, and you ended, you proposed the red rejected point. Now, I want to explain, this is going to be close to 1, because pi of x double primed is going to be close to pi of x, yeah? You started here, you bounced, you come back. This is the gradient direction. So these are the same height above the tangent plane. So that's going to be, the discrepancy between these two, or in the logs, is going to be order delta squared. Likewise, alpha x double primed x primed, that's going to be pi of x primed over pi of x double primed. This one is pi of x primed over pi of x, but because the posteriors are about the same height above the tangent plane, these two acceptance probabilities, again, the discrepancy in the log is going to be order delta squared. So if delta is small, this second acceptance probability is going to be order 1. And whether or not you accepted that, right, you flip at the end. So that, in fact, you're not heading back towards the rejection point, but you're actually heading away. So that is the second reversible algorithm. So 2 reversible kernels stuck together to give this non-reversible. How does it differ then? There is actually a chance you'll reject, and you'll have to go back the way you started, which is not the Bouncy Particle Sampler. One of the great things, in a way, is it seems to, it's rejection-free. Yeah, this, because it's discrete time and delta is not 0, then it's not. Now, interestingly, as delta tends to 0, so if you take smaller and smaller steps, and the number of iterations is proportional to 1 over delta increases, then the limit is the continuous time algorithm. Okay. The extended target, I guess it's fairly obvious. It's, again, the marginal is pi that you want, and the velocity is just uniform on the unit sphere. I think there was one other thing. Yes. So actually, you don't even have to bounce off grad log pi, the tangent hyperplane to grad log pi. You can use any vector field. Now, if you don't use grad log pi, you're going to increase the chance of rejection, and in the limit, you won't get the bouncy particle sampler, you'll get a bouncy particle sampler with rejection. But suppose grad log pi is expensive to evaluate and you want to use a surrogate. You can do that. And the algorithm is still valid. Yeah? You're still using pi in this step, but grad log pi you can use a surrogate for. So this is a reminder of our algorithm. I'm now going to show you Alexandra's Bouchard-Coates algorithm. It's explained slightly differently, so it fits in our context, but it is the algorithm Alexandra explained. So remember, what we've done is at the rejection point, we've calculated seen the tangent, hyperplane, and bounced off that. Now, with their algorithm, what you do is, here's the rejected point. You actually look at the contour on the last accepted point. And you put the tangent hyperplane to that, and you bounce off that. So now, how do you decide whether to accept or reject? You look and imagine from this blue point, if you were coming into the black point, and would you have rejected there? If you're the next, obviously from the blue, you go to the black, next you propose there, would you have rejected that? Because if you would, then you go back this way, and that's reversible. So you look at that point and see, would I have actually rejected it using the same uniform random number as I used in the accept reject here? So to do the accept reject, you pick a uniform between 0 and 1, you see if it's less than the ratio of the pi's. If you use the same uniform random number here, would I have accepted or rejected? And if you would have rejected, then that's great, because you would have just gone back the other way. And so you accept this bounce, because it's all reversible. If you'd have rejected, then you don't. And you reject, and you just go back the way you come. So that's the difference. Now, Christoph has given us yesterday a way of actually comparing these two algorithms and possibly seeing if one dominates the other. I imagine that's another paper for another time, but I'm not sure. My guess would be actually neither dominates the other. Okay, so here's the discrete bouncy particle sampler in action. Oops. So we started there. It's going to carry on like Gustafsson for a while, except as soon as we reject, we may well bounce. We might go back the way we started, but in this case, we bounced. Keep going in that direction, propose, keep going, reject, or have a stage 1 rejection, so we do the delayed, we bounce, propose that, oh, it's looking good, oh, what's going to happen, oh, we've double backed the way we were coming. Now, I should say, I wanted to show you it double backing, and it took quite a few different random seeds me trying before I could get this nice little demonstration to show you the double backing. So it's not that bad that it happens so frequently. It's actually double backed over 2. As you can see it, if you could see that. Yeah, it was going forwards and it's double backed, followed exactly the same trajectory. But actually this time it didn't reject at that point. It kept going, all right, and then it's bounced. So this is a standard MCMC algorithm, except it's non-reversible. Here's the ACF plots. You see these in several papers on the Bouncy Particle Sampler. And they look fantastic. Yeah. This is in dimension 25. I've just picked out 3 components at random, the 1st, the 10th, and the 25th. But since they're all the same, it doesn't matter. And it looks great. And I've thinned it by 10, and the effective sample size is bigger than the actual size of the sample I'm looking at. And it would even be if I hadn't thinned it. So this seems great, but actually, if you look at the trace plots, they're awful. All right. So this is because the velocity sometimes can take ages to mix across, and so when sometimes it actually even doesn't mix across the whole unit sphere, so you get a reducible algorithm. In the case I look at, well, I can't tell. Maybe it's reducible, maybe it isn't. And to give you an insight into that, here's, again, I had to try several random seeds to get this. This is 100 iterations of the discrete bouncy particle sampler, and you can see it bouncing backwards and forwards across here. So the velocity for a long time is not mixing much between that and that. Okay, so that's a bit of a problem. How do we get around that? So I'm going to say 2 methods to get around it. First is like Christian and Wu. It's one, but slightly different. So here's where we were. We proposed this. We rejected it. We have bounced. So we proposed that, we rejected, we did delayed rejection, and we've now proposed this. Okay? And the key to having almost 1 acceptance probability is that the height above the tangent plane here is the same as the height here. So you've gone the same distance in the direction of the gradient. All right? Well, there's a lot of other directions that would allow us to do that. All right? Anything on this circle in 3 dimensions, it would be the shell of a hypersphere, or a shell of a sphere in 4 dimensions, and so on. But actually, we don't want to lose the momentum we've got in this direction. Yeah? We don't want to lose that. So why don't I propose somewhere between these dots? So basically, an epsilon perturbation of the direction around this circle. Okay? And just for simplicity, I'm going to pick that one. But I can't just propose that. So, I should say it's got to be a symmetric distribution around this point, around the original sort of strict proposal. I obviously changed the velocity to fit that as well. And if you make that symmetric, then it turns out going back the other way, you're just as likely to propose this, because this will be kind of the other way off the strict bouncy particle sampler for that. All right, so that's reversible. And it works. It cures the jittering the velocity, actually cures the trace plots. But in the tests I did, and this was some time ago, it didn't work as well as what I'm going to say next. So I want to revisit those, the tests, but the ones I did, it didn't seem to work as well as this, which is every single iteration, after you've done it, and the iteration might be you proposed a move and you accepted, you proposed, rejected, proposed a bounce and accepted, or you actually rejected that. Whatever you've done, you perturb the velocity. You just jitter it a little bit. All right? So U goes to basically pick, well, it doesn't even matter. I keep U as a unit vector and I just perturb it slightly in a way that's going to preserve the uniform on the sphere. So I've got a parameter kappa, which is going to say how much I'm perturbing the velocity. All right? And the way I parameterize this is I want it to be easy to tune. All right, so I want the parameter kappa and the parameter delta to have orthogonal effects on the behavior of the algorithm. And if you imagine I've got a particular kappa, so I shift the velocity by this much every iteration. If I double delta, instead of taking, say, 8 jumps to get across the posterior, if I double delta, it's only going to take 4. I'm only going to have 4 perturbations, which is going to jitter the velocity less. I want it to jitter about the same amount in one crossing of the posterior. And this parameterization allows that. So that's what I've just said. All right, so here's what this algorithm looks like. And you can see it meandering about. All right? And even when it double backs, which it would have there, I think, it's not going on exactly the same path. All right? And it's just changing its velocity a bit as it goes across the posterior. Oh, a bit more. Oh, yeah, so that has, we rejected that. But we've gone off in that direction. Okay. Oh, is it going to stop? Yes. So the ACF plots look as good. Effective sample size isn't quite as good as in the previous, the straight algorithm, but you can actually believe it because the trace plots are a lot better. Okay. So that was a simple scale parameter is 1. Now I'm thinking of some kind of cigar-shaped target, just a little bit more difficult target. Oops. Oh, what have I done? Yeah. So I've got a scale parameter. I'm 25-dimensional. I've got a scale parameter of 25 in the 25th dimension, 24 in the 24th dimension, 1 in the 1st dimension. So it's an anisotropic target. And the worst effective sample size from the 10 to the 5 iterations was only 190. Random walk does much worse, I should say. And there's the trace plots. So you can see the 25th component isn't doing so well. And the obvious solution here is the same as you use for random walk, the same as you use for Mallet or HMC. If you know you've got a strange shape, let's just propose, all right, X is my real space. Let's just do get an X star, which is some linear transformation of X. In this case, if one of them is 25 times as long as the other, why don't I just shrink it by a factor of 25? So now it's back to isotropic. And if you do that, and you can imagine doing the bouncy particle sampler in this space, so you transform to the star space, then it all works fine, obviously. And what does that mean in the original space? This is just the formula in the paper, so there was no intuition in that paper I saw. It comes to a different geometry. The angle of incidence is no longer the angle of reflection. Okay, but otherwise it's basically the same. And obviously these are actually just the same trace plots I gave before. But this is actually what it does. I have checked my code too. All right, what diagnostics am I going to use to tune this algorithm then? So F bounces. You've done 10 to the 5 iterations. You had 1,000 delayed rejection steps. And 100 of those you actually rejected even the delayed rejection, but 900 you accepted and you did a nice bounce. Right, so the fraction of bounces would be 900 over 10 to the 5. Just how many of those iterations did you even try and do a bounce and actually succeed? So fraction of rejects is the one where you tried to do a bounce and you rejected it. All right, RMS dot. So we need a way of seeing from one rejection or one bounce or is just a rejection to the next one, which is basically, you know, a width of the posterior, how much you change. So how much does the velocity change from going from there to there? So if I look at the cosine of the angle between these, just by taking the dot product, well, if I found the average of that, it would be 0, because sometimes it's going to go that way, sometimes it's going to go that way. So if I square it and find the average of that, and then the root of it, then that actually gives something that's very sensible, because you can even kind of calibrate it. In dimension d, then this should be 1 over root d. So in dimension 25, if you pick 2 vectors at random, so basically if by the end you've lost track of the direction you're pointing at the beginning because your mixing is so much, then the root mean square angle between 2 random vectors in dimension d is 1 over root d, or the cosine is. So we get an idea of calibrating it. Finally, yeah, effective sample size, just for the graphs I'm going to show, it's the minimum over all the dimensions of the effective sample size, and typically that's the 25th dimension because that's the most stretched. Okay, so tuning delta. Delta is the step size, all right? How much in the direction u do you move each time? Let's just look at the number of rejections first. So this is if you reject the bouncy part, the delayed rejection proposal. So as delta goes to 0, this algorithm becomes the Bouncy Particle Sampler and it's rejection free. So when log 10 delta is minus 1.5, there's no rejections effectively. When log 10 delta is 1.5, then there's pretty much 100% rejections. So what that's meaning is you're crossing the space in one jump, and then you're proposing the bounce to somewhere over here, and you're hoping that the log posterior here and here are the same. Well, fat chance unless you've got some very nice symmetric distribution. What about this? Well, as I increase delta, what's happening initially is instead of taking me 8 jumps to cross the posterior, it's bigger. It's only taking me 4. I've still got the same number of iterations, and basically delta is still small enough that my bounce will be successful. All right? So as I increase delta, I've got more delayed rejection steps, and they're pretty much all successful. So I simply, in the same number of iterations, have more successful bounces. But as I get to this point, then the number of rejections starts kicking in, and my delta is so big that I might be crossing the posterior quickly, but I'm quite likely to then reject the bounce and just double back the way I came. And it won't be quite doubling back because the direction is changing, but it is still less efficient. Okay, so that's why this goes up and then goes down. Minimum effective sample size. So the thing to notice, and this happens across a lot of examples we've looked at, is it's maximized at about the same time as the number of bounces, as the fraction of bounces. And we have some heuristics for why this is the case, but there's just not going to be time to go into that. This is the so the angle between the starting and the end when it's crossing the posterior. And this is just basically showing, hey, it's about 0.85 all the time, apart from when delta is really big, so that we have succeeded in making the parameters effects orthogonal, the tuning parameters effects. Tuning kappa, so now I'm fixing delta, all right, and this is log kappa on the axis. And yes, so kappa isn't affecting the acceptance or reject, that's just the fraction of bounces because delta's staying the same. So it's taking the same number of iterations to go across, and the accuracy just depends on delta, whether or not you're going to accept. Okay? The effective sample size, again, has a maximum, and the maximum is at about, in this case, just below -1, so maybe just about 0.8. So the cosine of the angle between, effectively think of it as the cosine of the angle between the vector at the start of moving across the posterior and at the end is about 0.8. Right, so it's order 1. It hasn't gone down to the 0.2, which it'll tend to, okay, when kappa is really large. So it's saying the optimum thing to do is, yes, to jitter a bit, but not to jitter so much that you've forgotten where you are, what direction you were going. How long have I got? 5, 10 minutes. Okay, I think I might have time. Yay. Okay, so we didn't have to do the Poisson process for thinning, but we still have to calculate grad log pi to get at a bounce point to get the tangent hyperplane in order to actually bounce off it. Now, how do you get that? Well, if you've just got a GLM or something, that's analytical. It's fine. If you've got some kind of Kalman filter type algorithm, then you can still do it analytically. So linear noise approximation I've done. Mark Girolami and Ben Calderhead had a nice paper where they could find, showed you get the gradient and the information just basically with an algorithm analytically. There's a big thing nowadays, auto-differentiation. So it's something that takes your computer code and turns it into computer code, which is the gradient or the set of second derivatives. And the received wisdom when I started this was this can do anything. Okay? And so I tried it I was using Julia, I tried it on some simple targets, fantastic, it's all working, beautiful. And then the first real target I tried it on, which was the Markov modulated Poisson process, it fell over, and it wouldn't do it. And the reason is the likelihood for the MMPP has a load of matrix exponentials, and when I homed it down, it just wouldn't do matrix exponentials. So I asked Alex, who was working in Python using TensorFlow, and that wouldn't do it either. So I think this is great, don't get me wrong, but it's not the cure for everything. So what else? Well, I can always use numerical differentiation, good old Euler or centered difference, all right? And that will do pretty much anything if you get the step right. But that costs, if I'm in dimension D and I want to estimate the gradient, I've got to do D calculations, haven't I, to get all the components of the gradient. That's expensive. So can I do anything about that? Do I actually need to evaluate all of these? No. All right, so here's how to do it using how to do a bouncy step using a single random, well, it doesn't even have to be random. You can pick the vector in the start, but it seems more sensible to make it random. So, zeta, that's just going to be some unit vector you picked. All right, u is the current velocity. G I'm using to be short for the gradient. All right, and g hat to be the unit vector in the gradient direction. And what I'm going to show you is a transformation that takes u, that velocity in zeta, and gives you a bouncy v and the velocity. So there's a u coming in, and it's going to give you a v that would also be coming in, and then obviously the flip move will take that away. And it's going to be three things, and they're all important. I mean, the nice bit is it's going to be reversible. All right, so that if you went here and were to here, you propose this, then if you were coming in this way, you would have proposed this. Okay? It's going to obviously have it's going to be a unit vector, which we need, and it's going to, importantly for the acceptance probability being high with small delta, it's going to conserve the component in the direction of the gradient, without me evaluating the full gradient. And the key thing is to solve this equation. Now, actually, let's rewrite this. What I'm trying to do is write my velocity v as a linear combination of my velocity u and this new vector zeta. All right, that's the rearrangement of this. There are three unknowns, a, b, and v, and I've got three equations. And it's actually just a few lines to solve those equations. I'm not going to bother because it just looks like a mess, but you can easily solve them. All right, so we solve that equation subject to 2 and 3, and that will give us a velocity v. Yeah, exactly one solution. Unsurprisingly, what I need to know is the component of zeta in the g and the u direction, and the component of u in the g direction. So I need to calculate this and this, which is 2 evaluations of the derivative, not d evaluations of the derivative. Okay? Now, if you look at this setup, if I just swap a and u and b and v, just swap those pairs, I've got exactly the same equation, just relabeling. So I'm going to get exactly the same solution, which is why it's reversible. Okay? And obviously at the end, whatever happens, I'm going to flip the velocity. So here's what it would look like. I come in, I bounce, but instead of bouncing to over here, I bounce to somewhere else on that circle above the tangent plane. And where was zeta? Well, we know v is a linear combination of u and this zeta, so zeta's got to be in the hyperplane spanned by the u velocity and the v velocity. All right. All right, well, that's just one. That turns out to be quite inefficient because it depends where you choose your zeta as to how much of your momentum in that direction you're still going to preserve. You could easily go boink and then off in that direction. So, well, it turns out if you happen to choose zeta to be exactly minus g hat, so that unit vector is exactly minus the gradient vector, then you get exactly the bouncy particle, or discrete bouncy particle sampler. You get exactly the move that would preserve the momentum. Okay? Well, but we don't know g. All right, so I can't do that. I don't know the full gradient because I don't want to evaluate all d components of it. Well, I can just pick some random, instead of one zeta, I can pick a bunch of random zetas. All right, and I can construct, and each of those, maybe I have 25 dimensions, I could use 5. In each of those random zetas that are all orthogonal, I can look at the Euler, use the Euler method to get the component in the direction of the gradient, sorry, the gradient in that direction for each of those zetas. And then I just take the optimal linear combination that will get me something as close as I can to b minus g, which turns out to be this. This is just making it a unit vector, and this is just basically saying, hey, how much do I want u particular, zeta 1? Look how much you're in the direction, you go down in the direction of the gradient. All right, so here's some very quick results with this. What I've got here now, I'm on 25 dimensions. How many Euler components do I evaluate? Going from 0, or 1, in fact, up to 25. And the main thing to look at, so one thing is the tuning parameters don't really change much. Slight changes when you get down to 1 as to exactly what's optimal, but not a lot. But the main thing is, hey, I've actually made most of my progress quite early on, maybe 10 components. So I actually, if cost is important, I don't need to evaluate all of them. Similarly, I've tried this with dimension 100, and it's the same. You need 15 or 20 of the 100 components. Phew. I have hit time, so this is the summary, and it's just to say this is really exciting. I've got a 3-year postdoc position I'm about to advertise, so if you're finishing a postdoc or you're finishing a PhD and you're excited by this as I am, then come and talk to me. Thank you all for listening.
Do you have any questions for Chris?
Chris, so in Gustafson's original algorithm, I think he was moving a random distance at each point. Right?
Okay, yeah.
In your one, it's just, is it distance 1 each time?
That's
reason for that?
So I partly demonstrated it like that so that it would then fit into what we've got now. You can move a random distance, and this is one exciting area to look into. So you can imagine, one way of thinking of it is instead of your velocity being a unit vector, the length could also have a distribution. And this would allow you to do things like bounce up slightly less than you came down. This would be the same, but perhaps you could come up like steeper angle to get the same. Or equivalently, if you're in an anisotropic target and you want preconditioning, it could actually, I won't go into it, but it could actually help you there. Yeah, so you can, and you did, yeah.
If you're taking a random subset of gradient components, do you still need this epsilon bounce?
No. So The results I showed you were with the epsilon bounce set to 0. In fact, you might, because it's effectively doing similar to the epsilon bounce. And I sort of did compare those and did find, oh yeah, when I have like dimension 23 or 24 of the components, then it's pretty much like the epsilon bounce, because you're almost got the right direction. Whether you could probably take either this or the kappa or the epsilon bounce, but I've actually kept the kappa because the kappa seemed to be more efficient than the epsilon bounce. So having kappa and this might still help. I think I've checked that.
Okay. Well, next slide.